For thousands of years, the laws of physics stood as immutable guardians of reality. They dictated the fall of apples, the orbit of planets, the birth and death of stars. They told us what was possible and what lay forever beyond reach. And then, in a quiet laboratory in California, something happened that no physicist from Newton to Einstein to the present day could have fully prepared for. Google's quantum AI team ran an experiment on their Willow processor that did not merely push the boundaries of computation. It revealed a crack in the very foundation of how we thought the universe computes its own evolution. What emerged was not just faster calculation. It was a demonstration that certain physical processes, once believed to require resources spanning cosmic timescales on classical machines, could be probed directly, intimately, in minutes. The implications ripple outward from silicon and superconducting circuits into the deepest questions of matter, time, and information itself. This is the story of how a quantum machine, built by human hands, began to speak a language the universe has been using all along. The journey begins with a problem that has haunted quantum computing for decades. Qubits are fragile. They decohere. Errors multiply with scale. For years, the dream of useful, fault-tolerant quantum computation seemed perpetually just out of reach, trapped behind an error threshold that no one could reliably cross. Then, in December 2024, Google unveiled Willow, a 105-qubit superconducting processor. What it achieved was not incremental progress. It was the first clear demonstration of quantum error correction, operating below the surface code threshold on a scalable superconducting platform. As the code distance increased from smaller grids to a distance 7 logical qubit, using 101 physical qubits, the logical error rate was suppressed by a factor of approximately 2.14 with each step. The system achieved beyond break-even performance, where the encoded logical qubit preserved information longer than the best physical qubit by a factor of about 2.4. Real-time decoding operated with microsecond latency over 1 million cycles. These are not abstract numbers. They represent the moment when quantum hardware began to behave like a system that could, in principle, scale to the millions of qubits needed for transformative applications. But error correction was only the foundation. The true rupture came in October 2025, when researchers deployed the quantum echoes algorithm, based on out-of-time order correlators, OTOCs, on Willow. This computation explores quantum chaos and information scrambling, concepts essential to understanding black hole physics, quantum many-body systems, and the bridge between quantum mechanics and thermodynamics. On Willow, it completed in minutes what the Frontier supercomputer, one of the most powerful classical machines ever built, would have required roughly 10 septillion years to match in the relevant regime, a speed-up on the order of 13,000 times for the verified benchmark task. 10 septillion years exceeds the age of the observable universe by many orders of magnitude. This is not hype about generic supremacy. It is a verifiable quantum advantage on a physically meaningful problem in quantum dynamics, published and scrutinized in leading venues. The algorithm does not solve every problem, nor does it render classical computers obsolete overnight. But it demonstrates that quantum processors can now access regimes of physical simulation that classical methods cannot practically touch, even with the full resources of today's exasol systems. Consider what this means for our understanding of physics itself. Out-of-time order correlators quantify how quickly quantum information spreads and scrambles in a system. In black hole physics via the ADS/CFT correspondence, similar quantities relate to how chaos emerges near event horizons. By simulating these dynamics directly on a quantum device, researchers gain a new experimental window into phenomena that were previously the domain of pure theory or astronomical observation. The machine is not just calculating. It is letting us watch the universe rehearse its own rules at scales and speeds inaccessible before. This breakthrough did not arrive in isolation. It rests on years of meticulous engineering, improved qubit coherence, better control electronics, advanced cryogenic systems, and sophisticated calibration protocols. Google's dual-track approach, continuing superconducting work while expanding into neutral atom platforms in 2026, reflects a recognition that different hardware modalities will complement one another. Neutral atoms offer long coherence times and natural scalability for certain simulations, while superconducting circuits provide fast gates. Cross-pollination between these paths accelerates progress. The human element behind these machines is equally profound. Teams of physicists, engineers, and computer scientists have spent decades iterating on systems where a single misplaced photon or thermal fluctuation can destroy a computation. Achieving below-threshold error correction required not only better hardware, but also theoretical advances in decoding algorithms capable of operating in real time. The latency of 63 microseconds for distance 5 codes marks a practical engineering triumph. It means the system can detect, diagnose, and correct errors faster than they accumulate in meaningful ways. Yet, the deeper disturbance lies in what this reveals about reality. Classical computers simulate quantum systems using approximations that grow exponentially expensive. A quantum processor, by its very nature, inhabits the same Hilbert space as the systems it models. When Willow runs quantum echoes, it is not approximating the physics. It is enacting a tiny, controlled fragment of it. The boundary between simulator and simulated begins to blur in ways that echo the philosophical questions raised by early quantum pioneers like Bohr and Heisenberg. Observation, information, and physical law intertwine more intimately than our everyday intuition allows. In the months following these results, applications began to crystallize. The Replica program, launched in 2025 with a $10 million commitment across multiple universities including Harvard, MIT, and others, applies quantum AI to life sciences. Complex molecular interactions, protein folding dynamics, and quantum effects in biological systems become tractable. These are problems where classical methods hit walls of combinatorial explosion. Quantum simulation offers a path to new drugs, better understanding of enzyme catalysis, and insights into the quantum origins of life processes. Material science stands on the cusp of transformation. Designing room-temperature superconductors, novel catalysts for carbon capture, or high-efficiency solar materials has always been limited by our inability to accurately model electron correlations at scale. Quantum computers excel precisely in those strongly correlated regimes. Google's leadership has projected that within 5 years, commercial applications unique to quantum hardware could emerge in areas like energy, logistics, and fundamental science. This timeline contrasts with more conservative estimates, but is grounded in the exponential error suppression now demonstrated. Cryptography faces urgent implications as well. Shor's algorithm and its generalizations mean that large-scale fault-tolerant quantum computers could factor large numbers and break current public key encryption. Google has already outlined migration timelines to post-quantum cryptography, targeting 2029 for internal systems. The race between quantum code-breaking capability and quantum-resistant algorithms is no longer theoretical. It is a pressing security concern for governments and industry alike. These advances force a re-evaluation of what we mean by breaking physics. The laws have not changed. Gravity still pulls, Entropy still increases, quantum mechanics still governs the small. But our ability to interrogate those laws has crossed a threshold. Problems once relegated to the realm of, in principle, solvable but practically impossible, are now within experimental reach. This shifts the scientific method itself. Theory can be tested against direct quantum simulation rather than indirect classical approximation. Discrepancies between prediction and quantum output could reveal new physics, subtle deviations from standard models, or deeper layers of emergent behavior. The narrative arc of quantum computing has long been one of promise shadowed by skepticism. Early claims of supremacy with Sycamore in 2019 were powerful but narrow. Willow and quantum echoes move the field decisively toward utility. Error correction scaling below threshold confirms that the theoretical roadmap envisioned by Shor, Preskill, and others is physically realizable. The exponential suppression of errors with scale is the pivotal engineering confirmation that large logical qubit arrays are not a fantasy. Yet humility remains essential. Current devices, even Willow, operate with dozens to hundreds of qubits in logical encodings. Fault-tolerant algorithms for real-world problems like breaking RSA or simulating large molecules will require thousands to millions of physical qubits with even lower error rates. Noise, crosstalk, and correlated errors still pose challenges, as seen in rare events limiting repetition codes. Progress is real, measurable, and accelerating, but the path forward demands sustained investment, international collaboration, and rigorous verification. This moment also invites reflection on the nature of intelligence and discovery. Quantum AI systems are not sentient, but they augment human cognition in unprecedented ways. Machine learning assists in qubit calibration, error decoding, and even hypothesis generation for new algorithms. The interplay between classical AI and quantum hardware creates a feedback loop of discovery. AI designs better quantum experiments. Quantum experiments generate data that trains better AI. The boundary between tool and collaborator continues to evolve. As these systems scale, questions of simulation and reality grow sharper. If a quantum computer can faithfully reproduce segments of quantum field theory or condensed matter dynamics, what does that say about the computational nature of the universe? Some physicists explore whether the cosmos itself operates like a vast information processor. While speculative, the empirical success of quantum simulation lends tangible weight to such ideas. We are building miniature universes inside our labs and watching them unfold according to the same rules that govern galaxies. The practical horizons are equally awe-inspiring. Climate modeling at unprecedented fidelity, optimization of fusion reactor designs, secure communication networks based on quantum key distribution, and accelerated drug discovery for diseases that have evaded classical approaches. Each represents not science fiction, but near-term engineering challenges built on the foundations laid by Willow and its successors. The story does not end with one chip or one algorithm. Google's expansion into neutral atoms, partnerships with academic institutions through Replica, and continued roadmap toward larger-scale systems signal a field entering maturity. Other players, IBM, IonQ, Quantinuum, academic labs worldwide, and national initiatives in China, Europe, and elsewhere, contribute to a global ecosystem. Competition and collaboration together drive the pace. What makes this particular breakthrough feel like a rupture is its direct confrontation with time and scale. A computation that would outlast the stars, completed while you might brew a cup of coffee. It compresses the inconceivable into the everyday, forcing us to confront how limited our classical intuition truly is. Physics has always been about finding the simplest descriptions of the most complex phenomena. Quantum computing is giving us new instruments to write those descriptions more accurately than ever before. In the end, Google's quantum AI did not break the laws of physics. It broke the illusion that those laws were forever beyond our intimate experimental grasp. It showed that we can now build machines that dance with quantum reality on its own terms, revealing patterns and possibilities that were hidden in the exponential complexity of classical simulation. This is the dawn of a new chapter in human discovery, where the boundary between understanding the universe and participating in its computation grows thinner with every logical qubit stabilized. The universe has always computed itself through quantum processes. For the first time, we have built a mirror small enough, coherent enough, and fast enough to catch meaningful reflections of that computation. What we see in that mirror will reshape materials, medicine, energy, and our fundamental picture of reality. The question is no longer whether quantum computers will change the world. It is how profoundly we will choose to wield that change, and what new questions we will dare to ask once the mirror grows large enough to reflect the cosmos back at us. If this glimpse into the quantum frontier has shifted how you see the fabric of existence, the machines we build, and the future we are accelerating toward, then you are already part of the conversation. The next breakthrough may not come from a single lab, but from the collective curiosity of minds like yours, engaging with these ideas. Subscribe, share your thoughts in the comments, and stay engaged. Because the universe is computing, and for the first time, we are learning to read along in real time. What will we discover on the next page? The answer is being written right now, qubit by qubit, insight by insight, and we have only just begun to turn it.